computer. All right, let me go ahead and hide this screen. All right, floating panel control. And that one right there. And so that should give us a full screen of our. So we started chapter 6. In chapter 6, we're all learning about mechanisms. And the first thing we learned about was a reaction coordinate diagram that helps us figure out what's happening in each step of the way and what the energy associated with each step is. And then we kind of culminated that with rate laws. If you have a one hump on your reaction coordinate diagram, your rate law is second order because it depends on both components. Okay. If you have two humps on your reaction diagram, that's first order because you're waiting for the rate determining step, the step with the highest activation. Okay. Now, what we learned from that is that in our rate law, only varying the first component is important in a first order, but if you vary either component in a second order, you can increase the rate. If you increase one of the components, it'll double the rate. If you increase the other component, it'll double the rate. If you increase the concentration of both components, it quadruples the rate times 4. Okay, so does that make sense that when we have to have two things happening at the two things meeting in space at the same time, that we're going to get that interaction where they have to, by increasing that concentration, we have more of these interactions and it gets faster and faster. Okay, so now that's for reactions that go to completion, meaning that almost everything goes to products, but that's not for every reaction. Sometimes there's a back reaction. And when we talk about a back reaction, we have to talk about equilibrium, okay? And rate constants associated with the equilibrium means that the forward reaction has a 1 rate constant. We're going to call that K1. And the back reaction has another rate constant, K2. Okay. Now, let's think about our rate law. Okay. If we have a rate law for a second order reaction, the concentration of the two components are important, right? So if we're concentration for the stuff in rate law A, as the concentration goes down, the speed of the reaction goes down, right? But now the concentration of these is now going up. So that means the rate of the reverse reaction can speed up. So that's why if you have one rate law, it has to be much, much faster than the other rate law. Because as you build up concentration on the product sides, it's going to speed the back reaction up. And so what you'll end up with is instead of going to 100% or 99%, you're going to get somewhere around 80%, and then it's going to stop. Because the back reaction has enough concentration and enough speed to match the front reaction. And so when we have this right here, we have, instead of just the rate constant itself, we have actually an equilibrium constant. And that equilibrium constant is defined by either the rate of the forward reaction divided by the rate of the back reaction, or the concentration of products over the concentration of reactants. Okay, so does that make sense? That if it doesn't go all the way, you now have to look at two things, the forward and reverse, and it has everything to do with that, increasing the concentration, speeding up that second order rate law. All right, so that's the last thing I want to talk about that. Now I want to start talking about other ways that we're going to do mechanisms. And the first thing I want to remind you is that the bond between carbon and hydrogen is nonpolar. It doesn't do much, but all of the bonds with the halogens, fluorine, chlorine, bromine, and iodine, are polar. That's where we're going to do a reaction. We're going to use that polarity on that thing to make it important. But the other important thing is that the halogen is more electronegative, meaning that the carbon side is always partially positive. Write that down. The carbon side is always partially positive. And the halide side is always partially negative. That means when we have something that can come in to this partially positive side and make that halogen leave, we are looking at it from the point of view that the carbon here is partially positive. So we're going to be attacking it with a pair of electrons. Okay, we have a special name for that, and I'll get to that in a couple slides. Okay, so, that's actually on this slide. Nucleophile. Nucleophile, meaning it likes positive charge. Okay, And notice the nucleophile either has a lone pair or a negative charge. Okay, all nucleophiles have lone pairs or negative charges. If you see something with lone pairs and negative charges, think nucleophile. But in the acid-base reactions, what do we call them? We called them Lewis bases. Lewis base equals nucleophile. Lewis base equals nucleophile. Because it has a pair of electrons that it's willing to donate to make a sigma bond. That's the definition of Lewis base, right? That's also the definition of nucleophile. Okay, now, then we have the substrate. And in the case here, we're looking at just carbon halogen, okay? So our substrate is any carbon-containing substrate with a halogen on it. And we're going to call that halogen a leaving group, LG, leaving group. Okay, which means these electrons are going to come in and attack this carbon. The electrons that are on this bond between the carbon and the leaving group are going to leave with it, forming another nucleophile, forming another Lewis base, and in the process, creating a new sigma bond. So everything I told you about Lewis acids and bases is true for this as well. We're just changing the names. Our substrate is now our Lewis acid because the carbon has a partial positive charge. Okay, so we have a Lewis acid, a Lewis base, and our Lewis base, our Lewis acid, and a group that can leave. We form a new sigma bond and we form another nucleophile, another Lewis base. Okay, so there are 4 things to consider in this type of reaction. Number 1, what is the name of this reaction? We're replacing one group with another, so it's called a substitution reaction. Okay, so the substitution reaction, we are going to replace most of the time, we're going to start with halogens, but we can replace it with something else, and we'll get into that. We're going to replace the leaving group with the nucleophile and form our product. Okay, and we can form about 15 different compounds with this one reaction. And we'll show you that at the end of this chapter. Okay. There are 4 things that are important in this. Number 1, the leaving group ability. How stable is the leaving group? The more stable the leaving group is, the more likely it is to leave because it's happy. It doesn't have to use its electrons. It likes having. Number 2, the nucleophile type and strength. There's different types of nucleophiles: strong nucleophiles, weak nucleophiles, nucleophiles with just lone pairs, nucleophiles with just negative charges. And lone pairs. Solvent effects. Okay. That doesn't seem possible that a solvent could affect it. Remember, we have different types of bonding. Dipole, hydrogen bonding. Those are going to affect the reaction. And then the substrate. By substrate, we mean the nature of the R group. Is it primary, secondary, tertiary? Is it hindered? Is it benzylic? Is it allylic? You know, those are all going to be things that matter. So the general state of the reaction is any Lewis base, i.e. nucleophile, lone pair, will come in and attack the carbon on the other end of the polar halogen bond. Okay, it's not going to kick out a hydrogen. It's only going to kick out a good leaving group. When it does this, this forms a new sigma bond and a leaving group. Okay, we're going to talk about what drives this. Now we have an anion hitting the carbon, displacing an iodine. We have a methoxide. This is the deprotonated form of alcohol. We talked about that in acid base. And then it's going to attack this carbon, not this carbon, because this carbon doesn't have any polar bonds. It's only going to attack this carbon. So that's why it's here. And we're going to make an ether and the bromide. And we can even do a crazy reaction where we take a weaker nucleophile and displace a stronger nucleophile using solvent effects. So this is the same reaction. This is all substitution. It follows the same rules every time. These are all second order reactions that we're going to talk about here. Okay, they're going to be all second order reactions until our substrate changes. Then we're going to have first order reactions. So we had to pay attention to our substrate for them. Okay, so that being said, let's talk about nucleotides. Again, Lewis base. things that are good nucleophiles tend to have a negative charge. The more localized that negative charge, the better the nucleophile. They tend to have a counterbalancing ion. It can be anything. And as organic chemists, we really don't care about that much because it's not the organic part. It's just we're going to throw it away with the other reaction anyway. But there's usually some counterbalancing ion here. And so we're going to have the negative, these lone pair come in and create our new sigma bond. This sigma bond is going to create a lone pair on the bromide. And so that's our leaving group. Okay. Now, do you have to have a negative charge to be nucleophile? No, you can have Lewis bases that are not negatively charged, right? Anything with lone pairs can be a nucleophile. They might not be as strong, but they have a lone pair. Anything that's a Lewis base, anything that has a lone pair can act as a nucleophile. Now, in this case here, we're going to use excess of a nucleophile that's neutral, because when you start with a nucleophile that's neutral and you attack here and leave here, you end up with a substrate that has a positive charge. Notice when we started with a negative charge and a neutral substrate, we ended up with a neutral substrate and a counterbalanced charge. We don't have that counterbalancing charge yet, but now our nucleophile can also act as a base. Deprotonate this to give us our neutral product. So sometimes, I mean, anytime you have a neutral nucleophile, you have either a positively charged substrate or you have a second step to remove a proton. Okay, that brings me to my steps in a mechanism. Look at it on canvas. Add a proton, take a proton away, attack a nucleophile with an electrophile, break a bond to form a stable molecule or ion, and rearrange. If you do any other thing than that in our mechanisms, you are not following instructions. Those are the only things we can do, okay? There's a sheet on there on Canvas, so double check that and then figure out what each of those steps means. Okay. So let's talk about some common nucleophiles. Anything with a negative charge can tend to be a nucleophile. Anything with a lone pair can be a nucleophile. But they're divided into classes, okay? There's 4 things that make a nucleophile good or bad. Okay, so the other thing here is that think about all the functional groups we can make. If we attack with this, we're going to make an alcohol. If we attack with this, we're going to make an ether. If we attack with this, we're going to make an ester. If we attack with this, we're going to make an alcohol that's protonated. If we attack with this, we're going to extend our carbon chain. If we attack with this, we're going to make a chloride, an alkyl chloride. So we just did a whole bunch of different functional groups, all with the same reaction. Okay, so let's talk about the leaving group. Okay, in acid base, we should have learned, and I hope we did, that you always go from the stronger acid to the weaker acid, right? Stronger acid to weaker acid. That's the driving force. Okay, we're going to use that concept to see which way the reaction is going to go, because we want to go from the stronger acid, or in this case, the weaker conjugate base versus the stronger conjugate base, to drive it to completion. So we're going to have a substitution. We're going to have creating a new sigma bond. We're going to break an old sigma bond, creating this. So, but the leaving group has to be weaker nucleophile and tends to be a weaker base than the nucleophile we attacked with. The nucleophile needs to be, the leaving group has to be a weaker base than what we attacked with. There's one exception to that, but we'll talk about that. We're going to talk about halogen leaving groups, but we can actually use a bunch of different leaving groups. In chapter 7, we're going to learn that we can use water as a leaving group. But we're going to use halogens for this chapter just to make sure we understand the mechanism first. Okay, so the leaving group has some issues. Okay, there's some general trends. Unfortunately, basicity and nucleophilicity are not identical. They are different because remember, basicity is a thermodynamic product because in basicity we have equilibrium. Okay, in nucleophilicity, it's kinetic. Okay, So they usually trend together, but not always. So we need to pay attention to that. So the first thing we have to think of is with increasing basicity, it decreases our ability to leave. Okay, let's look at the periodic table. Okay. Just along this row right here, fluoride's a better leaving group than oxygen because this is a stronger base as an anion. Then oxygen is a better leaving group than nitrogen. And nitrogen is a better leaving group than carbon. Carbon's a horrible leaving group. You hardly ever have carbon leave. So that's telling us that as we go along a row, our leaving group ability increases as we go to the left. Our leaving group ability increases as we go to the left, go toward fluorine. Okay. My left. Not. Now, as we go down a column, what happens? Things get bigger, right? And as they get bigger, they're more polarizable. So as they get bigger, they're better leaving groups. Increasing leaving group ability increases with size because the increasing size made them stronger acids, which makes them weaker conjugate bases. So these are getting weaker as bases, and therefore they are better leaving groups. Again, it's that whole driving force. We want to go to the weakest acid or the weakest base. Okay, so it follows with our acid-base theory, right? Okay, however, there's some things we should pay attention to. Okay. Good leaving groups were things that were strong acids if they were protonated. HI, HBr, HCl all have pKa's below 0. And water actually turns out to be a good leaving group if it's protonated because its conjugate acid was the hydronium ion, which also has a pKa below 0. So everything that was a strong acid as an acid is now a great leaving group because it's a weak base. Okay. Now, as we go above 0 on our pKa for the conjugate acid, we start losing its ability. In fact, we get worse and worse and worse and worse. Fluoride is a worse leaving group than water or HCl. Hydroxide is worse than fluoride. R group, a carbon with a negative charge, is a horrible leaving group. You hardly ever see it. Okay, so I said that nucleophilicity and basicity are different. Okay, so in the case of basicity, it measures your ability to accept a proton, right? And that's in equilibrium, a thermodynamic property. In the case of nucleophilicity, it measures how fast it wants to donate its pair of electrons to form a sigma bond, which means it's characterized by a rate constant, making it kinetic. So basicity is thermodynamic, nucleophilicity is kinetic. They trend most of the time, but there are examples where that is not true, and that's what I'm going to draw attention to here. Okay. Negatively charged nucleophiles are usually stronger than neutral nucleophiles. Makes sense? Electrons, you want to use them. Okay. OH is a stronger base than water. OH minus is a stronger base than water. Nucleophiles with the same nucleophilic atoms are measured by their strength. Which one is the stronger base? If we look at water and if we look at acetic acid, which are the conjugate acids here, water is a weaker acid than this. That makes it a stronger base. So this is a stronger nucleophile. The hydroxide is a stronger nucleophile than the acetate. Because it was the weaker acid, it's the stronger base, it's the stronger nucleophile. Okay, so let's look at this series here. RO minus, deprotonated alcohols, pK is just slightly higher than water, are stronger nucleophiles than hydroxide, which are much, much stronger than acetate, which is much stronger than the neutrals, because the neutrals have to lose a proton at the end. Okay, so that means that as we go out here, increasing basicity will increase that nucleophilicity. So we're not talking about leaving group abilities. These would be horrible leaving groups, but guess what? Because they were bad leaving groups, they're great nucleophiles. Because they want to use those electrons to make that sigma bond. They really want to use that. So as we go across the row toward carbon, it increases nucleophilicity. And so that's the opposite of leaving group, by the way. All right. So But there are some other effects with nucleophilicity. Okay. In the case of our nucleophile, we have to be able to have that nucleophile come in and interact with the carbon while it still has 4 things bonded to it. That means that if you have too many bulky things on the carbon we're trying to attack, it will slow the reaction. That makes it harder to attack. So we call that steric hindrance. Okay. So in the case of this compound here, we only have 2 hydrogens and a methyl group here, meaning that our nucleophile can come in and attack. Oh, this is nucleophile strength. So the decreasing activity, because in this case here, we have a very small group, we have our anion here, and we have a lot of negative charge. It can be seen from a whole bunch of area here. We can see this negative charge from this whole side right here. But if we bulk it up, so we replace 2 of those hydrogens with methyl groups, now it can only be seen from the one little place where the 3 methyl groups aren't shielding. These are acting like an umbrella and making it so only a little bit of this anion can be seen. Here, these aren't shielding, so we can look at the full area as where it can be seen as an anion. So we call that steric hindrance. So the smaller the groups you have around your negatively charged species, the more nucleophilic it's going to be. In fact, this right here, write this down. T-butoxide, we call a non-nucleophilic base. It is so sterically hindered, it almost never acts as a nucleophile. It almost always acts as a base. And that's because of steric hindrance. Non-nucleophilic base, T-butoxide, almost always acts as a base and not a nucleophile. Okay. So let's talk about solvent effects. So the first thing we have to talk about solvent effects is whether the solvent is protic or aprotic. A protic solvent is something with a hydrogen bondable hydrogen. Okay, so we're not talking about the lone pairs that can be hydrogen bonded to. We're talking about the hydrogen that can actually do the hydrogen bond. It has to be a hydrogen on an oxygen or a nitrogen or a fluorine. Okay. So if we look at our protonated solvents here, we have a hydrogen on an oxygen in acetic acid. We have a hydrogen on an oxygen in T-butoxide, in butanol. We have a hydrogen on oxygen, a hydrogen on oxygen, a hydrogen on oxygen. Those are all protic solids. Those all can hydrogen bond. Okay, but now we also want to look at a class of solvents called aprotic, no hydrogen bonding proton. Okay, so all of these are going to see lone pairs or a permanent dipole moment. So we have dipole-dipole interaction, right? So in this case here, we have a permanent dipole moment, but no hydrogens on heteroatoms. None of these have hydrogens on heteroatoms. Most important ones are acetone. THF or tetrahydrofuran. It's a really good solvent for a lot of reactions. DMSO, dimethyl sulfoxide. It's a high boiling one, just like acetone, the sulfur analog of acetone. And then we have 2 amides here, DMF and DMAC, or dimethyl formatted. And again, these are kind of, if you think about it, these are carbonyl analogs. So we have a lot of carbonyl analogs that act as aprotic salts. No hydrogen on a heteroatom of oxygen or nitrogen. Okay, so why is that important? Well, because protic solvents can solvate both anions and cations. Because in the case of the hydrogen side of water or a protic solvent, that hydrogen can stabilize a negative charge by putting a whole bunch of them around it, creating a solvent cage. And we talked about that in our ion dipole or ion hydrogen bonding interaction. But what if you had a positive charge? Well, you have lone pairs hanging off these. These can act as stabilizers for a positive charge. So it can solvate both positive and negative ions. Okay, that's important. It can solvate both positive and negative ions. All right, let's look at our aprotic solvents. Okay, in our aprotic solvents, it only has a dipole interaction and you can't get as many around it, meaning that charge is less counterbalanced by the solvent, meaning it's more nucleophilic. So In the case of water, aprotic solvents, things that can hydrogen bond, are less nucleophilic. In aprotic solvents, things that don't hydrogen bond, are more nucleophilic because of that stabilization of that negative charge. Okay, so let's get this all on one slide to make sure we're not doing anything here. So all on one slide, the first thing we want to do is that polar protic solvents, okay, the nucleophilicity goes down as the ion size increases. Okay, so the nucleophilicity in a polar solvent goes down. But if we look at increasing basicity and aprotic solvents, they are parallel always. Okay, basicity and aprotic solvents are the same trend. Okay, but the one that's opposite of basicity is protic solvent. So we want to look at that really strongly. Now, in the case of polar aprotic solvents, that means we just look at basicity. And in basicity, we have the idea that fluoride is more or less basic. It was a weak acid, so that makes it a stronger base, which means it's going to be more nucleophilic than fluoride, which is more nucleophilic than bromine. But that's backwards from here. Look, iodine is more nucleophilic than bromine, which is more nucleophilic than chlorine, which is more nucleophilic. So it's very important to identify the solvent as protic or aprotic. Questions on that? All right, good. Oops. I'm going to have to change that brush stroke. It's a little wide. Let's go back to that one. Oh, actually, that one. Okay. Okay. So now let's look at our ways of doing our reaction. What has to happen is that we need to break a sigma bond and form a new sigma bond. Okay. So how can we do this? Well, one thing we can do is what we call a substitution reaction, where we're making and breaking a bond at the same time. Imagine your nucleophiles coming in and trying to make a bond. Your leaving group is saying, hey, I got to get out of here, and takes its electrons with it. We call that simultaneous. It's also known as a concerted reaction. It happens all at one time. Making and breaking all at one time. Okay. The other thing we can do is we can just break that bond first. Okay. So in those 5 steps of the mechanism, one is attack of a nucleophile by an electrophile. The other one is to break a bond to make a stable molecule or ion. So that's another thing we can do here, break a bond to make a stable molecule or ion. And then we have attack by a nucleophile. Well, but maybe we should just make the bond first so everybody knows where it is. Why can't we do that? We'd have 10 electrons around carbon. We would break the octet rule. We cannot do that. Boom, boom. Oh, not that one. Okay, so right here. We cannot have 10 electrons around carbon, therefore we cannot make the bond first. So we only have 2 options. We can make and break at the same time, or we can have something leave. So that means we have 2 mechanisms that we can play with to do these reactions, these substitution reactions. Okay, so let's look at the first one. Bond breaking and making at the same time. Okay, so if we're making and breaking at the same time, that means that both of the compounds have to be at the same place at the same time, right? So that means it's a second order reaction. Okay, now when we're looking at this, we also have to pay attention to the fact that we're going to have to go through a transition state that involves the partial forming of a bond and the partial breaking of a bond. Okay, now look at also where the nucleophile is coming in. The nucleophile is coming in 180 degrees from the leaving group. That means if these hydrogens or these start to get big, we're going to have problems. Remember, we talked about steric effects. We're going to have more problems. So what we're going to do is we're going to make and break bonds at the same time during our transition state and form our product. So that means we're going to have a second order reaction. We're going to have one hump on our reaction diagram. And our rate law is obviously going to be both components. And we call this a nucleophilic bimolecular substitution. So we have a S for substitution, N for nucleophilic, 2 for bimolecular. You could also say 2 for second order. But bimolecular is what's really cool. Okay. So that's one way we can do it. And so if we look at our energy diagram, we have one hump, one transition state that is forming and breaking at the same time, and we have cascade down to products. Okay. Questions on that? Okay, so that makes it fairly interesting to do. Now, what we saw here is look where our nucleophile is coming in. It has to come in at 180 degrees from the thing that's leaving. Why? Because the electrons have to be making the bond opposite where the electrons are leaving. You can't have them all coming in at the same place and leaving at the same place. So we're actually having them come in from the opposite side of where they're moving. So what does that do to our stereochemistry? Because we have to come in from the 180 degrees from our leaving group, and it's occasionally called the backside attack, it has to come in 180 degrees here. And what happens is now your groups here invert. So that means SN2 reactions have stereo-specific reaction because we get inversion. If you start with an R, you're going to end with an S. You get stereo inversion. Okay. So this is a stereo-selective reaction because it only forms one stereo isomer. Okay. So we can do that again with this here. And again, because the leaving group is here, we actually are attacking from this side on here to give us our inverted product. Okay, questions on that? So SN2, substitution nucleophilic bimolecular, second order rate law, one hump on the energy diagram, and inversion of stereochemistry. And it happens, that's every time. All that is true, every reaction. It's SN1. So we said there's effects. There's a solvent effect. There's a substrate effect for these reactions. In the case of substrate effects, because we have to have that bond forming 180 degrees from our leaving group, the bigger the groups get, the slower the reaction goes. So if we look at a methyl group here, those are 3 hydrogens. Those are easy to get around. And boom, it's the fastest to react. Well, let's put another CH3 here, maybe. That's a little bit bigger than hydrogen, so it's harder to get to. So it's not as fast, but it's still pretty good. And if we have 2 of them, we still have a hydrogen, so we can still kind of squeeze in there, but it's slower because it's harder to squeeze in there. And by the time we get to the third, it almost never happens. Because now you have 3 big bulky groups. Imagine an umbrella and trying to invert an umbrella from the top using just your finger. You don't have enough place to get in there and make that bond. Okay, so this is a huge umbrella protecting the backside of this, so this group can't move with an SN2 reaction. Okay, so what that means is that methyls and primaries will easily undergo SN2 reactions and very fast. If they're not too bulky, secondaries will also go. So if you have 2 groups or 2 big groups, it's probably not going to go very fast at all. But if you have a tertiary alkyl halide, they don't undergo them at all. So you have to do some other mechanism. Okay. So let's talk about that energy diagram again. Okay. So the higher the activation energy, the faster or the slower the reaction. Faster, slower, higher activation energy. Higher activation energy, the slower the reaction. Lower the activation energy, the faster the reaction, right? So if it's easier to get to this transition state because we have less bulky groups, the activation energy is lower. The energy is high because it has to squeeze itself in. If you put even 2 methyl groups on here, we're having to just squeeze past 2 much larger groups. And so therefore it's a higher activation energy, therefore it's a lower reaction rate. Okay. So that's SN2. We make and break a bond at the same time. Okay. Now, what if we want to do it the other way? What if we want to break the bond first? Okay, that's going to be SN1, substitution, nucleophilic, unimolecular, or first order rate law. You can use either one of those, okay? But it's truly unimolecular, one molecule. Okay. So what we have happen here is our first step is the slow step, breaking a bond to form a stable ion or molecule. And we form what we call a carbocation, positively charged carbon. And then this is very reactive, and we'll see that by the energy diagram. And so it reacts very quickly with anything. And in this case, it reacted with neutral water. And so when it reacted with neutral water, we ended up with a positively charged substrate. And when we end up with a positively charged substrate, we have to lose a proton to get to our final product. So our rate law here is a 1 first order rate law. Okay. So what makes this reaction happen? Well, it turns out that because we can't do SN2 reactions on tertiaries, we're going to do SN1 reactions. These are going to be faster. And then the secondaries can do it, but they're not as fast. And methyls and primaries hardly ever do it, okay? They don't undergo SN1 reactions, okay? Now, this is exactly opposite of SN2. There has to be a reason, right? Because the SN2 is all about sterics. The less sterics you had, the faster the reaction went. The SN1's all about the stability of the intermediate you form. You have to break that bond first. How easy it is to break that bond tells you why. So what we're going to talk about here is we're going to look at that intermediate we're forming. In the case of our unimolecular reaction here, we have to break the carbon-bromine bond to form an intermediate. So here's our transition state, here's our transition state, and we had to form an intermediate. Then we have a second activation energy to get to the second transition state to give us our product. Okay, so everything has to do with the stability of our intermediate. If our intermediate is too unstable, we won't form it. So we're looking to form the most stable intermediate we can. Okay, so we're looking to form the most stable carbocation we can. So what stabilizes a carbocation? Turns out that the more substituted your carbon is, i.e. tertiary alkyl halide, the more stable the carbocation will be. Okay, so tertiary carbocations are most stable, followed by secondaries, followed by primaries, and methyls are least stable. In fact, these are very unstable that you can't even make these in solution. You can only make them in gas phase. So we're not going to see those in reactions at all. So we don't even care about forming these because they're not stable. So we want to form tertiaries or occasionally secondaries. These are the only two that are going to do SN1 reaction. Okay. Now, why? There's two reasons why carbocations are more stable when they're more substituted. The first thing to do has to do with inductive effects. Remember when we talked about basicity and acidity? We're talking about pulling electrons or pushing electrons through sigma bonds. Okay. So in this case here, because the carbocation in the middle is now electron deficient, the other carbons are trying to donate a little bit of their electron density to it to help stabilize that positive charge. So it's trying to spread that positive charge out over 4 carbons through those sigma bonds. Okay. Now, when you have 2, you can do it with 2 of them here, and hydrogen doesn't contribute because it can't. It only have the 2 electrons anyway. There's no way it can contribute. And when we have 2 hydrogens here, again, we only have 1 carbon donating, making it even less stable. And then these are really not even stable. So we have the first effect is the inductive effect. Being able to push electrons back to that positively charged carbon. Okay, so then the other thing we have is hyperconjugation. And we have hyperconjugation because of the hybridization of our carbocation. So write this down. Carbocations are sp2 hybridized with a p with 0 electrons in it. Okay, sp2 hybridized, meaning it's trigonal plane, and it has an unhybridized p above and below the plane. and that p orbital is empty. Okay, so this is going to tell us something about its reactivity. This is going to tell us something about our product. So we need to make sure we understand that we have a lobe on the bottom is equal to the lobe on the top. And there are no electrons there. So the 2 electrons coming in from our nucleophile are going to form the bond. Okay, so what does that mean? Well, because we have a p orbital, we can line it up with at least one of the sp, come on, oh, there you go. One of the sp3 hybridized bonds to form the sigma bond of the hydrogen. It's close enough that it can partially give a little bit of electron density through space. That's called hyperconjugation. It's not transferring electrons, it's just donating a little bit of electron through space. Now, if you only have one methyl group, only one of them can donate. If we add another carbon here with a hydrogen here, we can donate some more on this side. So we have 2 hyperconjugation donations. And if we put a third carbon here, we can have 3 hyperconjugation donations. 3 different inductive donations plus 3 individual hyperconjugations stabilize it even more. So each step you stabilize it by adding a carbon next to the carbocation. So that means that our tertiary butyl carbocation here has 3 hyperconjugations and 3 inductives, 2 hyperconjugations, 2 inductives, 1 and 1, 1 and 1, 1 and 1. So we're not going to form these. So we're only going to do secondary and tertiary carbocations. Okay. Now, secondary carbocations aren't as stable as tertiary carbocations. So one of the things we can do in a mechanism is rearrange. Okay. So if a secondary carbocation isn't as stable as a tertiary carbocation, it's going to move if it can. A secondary carbocation will always rearrange if it can, but it has to follow one of 3 rules. Okay. The first rule we call is the 1,2 hydride shift. If you can move the carbocation over 1 carbon by just moving a hydrogen over 1 space to make a tertiary carbocation, it will. That's called the 1,2 hydride shift. Okay. We're moving 1 hydrogen, 1 carbon over to make a more stable tertiary carbocation. Okay, so that can happen only in our SN1 reaction. It's going to take this reaction and say, okay, wait a minute. I'm a secondary carbocation. If I move this hydrogen over 1, so let's look at this hydrogen right here, moves over 1 to get there. I'll have a tertiary carbocation. Okay, so that means if this compound, this secondary substrate, is undergoing an SN1 reaction, we're going to get a product with the nucleophile attacking the tertiary carbon. But in the case of SN2, sorry, we don't form the carbocation, and therefore we can only substitute on the carbon where the leaving group is, meaning we end up with a secondary. We end up with a secondary right here. Okay, so let me put it right here. So we can tell which mechanism it went through by what products it got. If it didn't move, it must have been SN2. If it did, a secondary did rearrange, it must be SN1. Okay, so we can only move 1 group over 1 carbon to make it more stable. You're never going to go from a secondary to a secondary. Only secondary to tertiary. Okay, only secondary to tertiary. And the first way we can do it is the 1,2 hydride shift. What if you don't have a hydride available? Well, you can do what's called a 1,2 methyl shift, meaning we can move a whole methyl group over. Man, that seems like a lot of trouble to break a bond and make a bond just to get it more stable, but that's how much more stable it is. That's how much more stable it is. It's going to do it. So in this case here, we're going to break the bond between the bromine and the carbon here first, giving us our secondary carbocation. And then what's going to happen is our secondary carbocation is going to say, wait a minute. It's going to move this methyl group over 1 thing, so it gives us a tertiary carbocation. And now that tertiary carbocation is more stable, it's going to react with the nucleophile, and it's going to give us our products. So it's the 1,2 methyl shift. 1,2 methyl shift. So we can only move one carbon. We can only go from a secondary to a tertiary carbocation. Okay. Now, what's the last way we can do this? Well, turns out we can do not just a methyl group, but we can do, oh, sorry. I wanted to reiterate this. Your secondary carbocation will only ever convert to a tertiary carbocation. It's not going to skip over an atom. We can't do a 1,3. We can't do a 1,2 and go to another secondary. You can only go from a secondary carbocation to a tertiary carbocation. Okay. And only moving one carbon, 1,2, 1,2, 1,2. Okay, the last kind of thing we can do is what we call a ring expansion. This is technically a 1,2 methyl shift with a twist. Okay, the twist is if you have ring strain, a 4 or 5 membered ring, it is going to want to eliminate the ring strain and open up. And so it's going to move the carbon that has ring strain first. So it's like a methyl shift, but it's called a ring expansion. Okay. So in the case of this, we have a 5-membered ring. 5-membered ring has more ring strain than a 6-membered ring. Okay. If you have a 6-membered ring, it will not rearrange. It has no ring strain. Okay. So what's going to happen is we're going to move these electrons over here to create our new bond. In the process, creating our carbocation. But then, of course, now we have to rearrange ourselves and we turn into the 6-membered ring. And then our nucleophile comes in and reacts. Okay. This only occurs in 3, 4, or 5-membered rings. No other rings. 3, 4, and 5-membered rings will do ring expansion. This is the real N95. The pharmacist gave them to me. So that's good. All right. So let's talk about that structure of that carbocation. The carbocation has an empty p orbital. So half of the p's on the top and half of the p's on the bottom. So is the nucleophile always going to attack the top? No. Is the nucleophile always going to attack the bottom? No. It's going to be 50-50, which means you have 50% S, 50% R. You always racemize when you go through a carbocation. You always racemize going through a carbocation. Always racemize going through a carbocation. So this is not a stereoselective reaction. It is a random reaction. Okay. So I'm going to skip those 2 slides. So now, how do you know which mechanism your reaction is going to do? You want to be able to predict your product, right? So you want to see, what's it going to be? So we want to predict whether it's going to go SN1 or SN2. And so we want to look for 3 things. Substrate effect. Can you form a stable carbocation? If you can't, probably not going to go SN1. Nucleophilic effects. If it's a strong nucleophile, then you might want to think SN2, but if it's a hindered nucleophile, we might have to go SN1. Solvent effects, protic or aprotic. Remember, protic solvents support cations and anions. Protic solvents promote cations, solvate anions and cations. That's important. So, in increasing orders of importance, substrate effect is first. Your tertiary and your secondary are probably going to go SN1. Your methyls and your primaries are probably going to go SN2 because of sterics. Nucleophile effects, strong and weak. The weaker the nucleophile, the more likely it's going to go to a SN1. Solvent effects, if it's protic, it's more likely to go SN1. So let's talk about each of these in order here. The most important factor is substrate. Okay. So in the case of substrate, methyls and primaries only do SN1. Okay. They do not do, I'm sorry, that is not true. Methyls and primaries only do SN2. Okay. So when we talk about that, we want to say that really, these don't do SN1 reactions at all. They only do SN2s. Okay. Now, the other thing we want to pay attention to is that tertiaries only do SN1 and never do SN2. Tertiaries only do SN1. Okay, now that leaves us with the thing here. We have an SN1 and SN2 that can both happen on that secondary substrate. So now we have to look at the next two important things. What are the next two important things? Nucleophile strength and solvent. Okay, so we're done here. These are going to always be, primaries and methyls are always going to be SN2. You don't even have to think about it. Automatic. Your tertiaries are always going to be SN1. Don't even have to think about it. The only thing you have to think about is secondary substrates. And now we move on to the next most important thing, nucleophilic strength. So what effects are our nucleophile? Well, in an SN2 reaction, if we have a strong nucleophile, think negative charge. Strong nucleophile, negative charge. It will undergo an SN2 reaction because it's kinetic. It'll undergo an SN2 reaction because it's kinetic. Remember, the slow step on an SN1 is breaking the bond. So if your kinetics are faster to substitute, it will. So the higher the nucleophilicity, the higher the kinetic strength, the faster the reaction will go as an SN2. If your nucleophile is bad, and it just has to wait around until a positive charge is formed, it's going to go SN1. Think uncharged species, water or alcohol. So we're going to see our production now. So if we end up going SN1 with a strong nucleophile, SN2 with a strong nucleophile, we're going to get one product. It's a stereoselective product, an inversion product. If we have to go through the SN1, we had to go through a carbocation, half on the top, half on the bottom, half one isomer, half the other isomer. And in this case, they're geometric isomers. Okay. All right, questions on that? So think if it's got a negative charge, it's probably going to do SN2. If it doesn't have a negative charge, it's probably going to go SN1. All right, and then solvent effects. Protic solvents like alcohols and water, okay, not only are they protic, they are also weak nucleophiles. So typically you use the solvent as the nucleophile. So when you have your protic solvents, you're going to favor an SN1 reaction. So that means if you have a secondary substrate or a tertiary substrate, you want to use a protic solvent. Now, if you have aprotic solvents, acetone, DMF, DMSO, DMSE, it favors the SN2 reaction because it doesn't support the cation. It doesn't support the cation, and therefore it forces the nucleophile to be more nucleophilic and makes it only do SN2. Aprotic solvents will do SN2 on secondary substrates. Protic solvents will do SN1 on secondary substrates. Okay, so the last thing we have to worry about is our leaving group here. So to form the carbocation, we have to break the bond. So the weaker the bond is, or the more polarizable the bond is, the easier it is going to be to break. Okay, so let's think about the fluorine here. It's very small. It has a very tight bond with carbon, right? Then let's think about iodine. It's very big. It has a very long bond with iodine. Okay, the bigger the leaving group is, the easier it is to break that bond. Therefore, the rate of the reaction increases as the polarizability increases. This is leaving group, not nucleophile. Remember, the halogen in nucleophiles are opposite in protic solvents versus aprotic. This is leaving group. This is not nucleophile. But the increase always increases as you get to a more polarizable bond. Okay, now I said that carbocation stability is key here. Okay, and when we talked about conjugation, we found out that we could write little resonance, we could write different resonance structures for different compounds here. Turns out that when we have things that have sp2 hybridized carbons, they do not undergo SN1 or SN2. You can only do SN1 and SN2 reactions on sp3 hybridized carbons. Only sp3, okay? Which means these will not react there, okay? But if you move one carbon away, have that double bond one carbon away, and it's sp3 hybridized, what happens is we actually have more stable carbocations. We can form a carbocation here, a carbocation here, and it will be in resonance with the double bond here, and it can go back and forth, meaning it's going to be stable. And we can do the same thing with these benzylic groups by forming the carbocation here outside the ring. It can be stable. Okay, that means that if we're one carbon away from a double bond or a triple or a benzene ring, it's going to be a very stable reaction. And again, the primaries and secondaries usually go SN2, but tertiaries and secondaries usually go SN1. Okay, so to summarize, SN1 requires breaking a bond first. Therefore, it works best with weak bases and protic solvents. SN2 requires a lot of stuff not being 180 degrees from the leaving group. So sterics is most important. And then we usually want a strong nucleophile to make that reaction happen quickly. And we want a protic solvent, so we can't support a cation. All right, so if we want to do a full summary on all these, SN2 is a bimolecular reaction, second order reaction, and one step. SN1 is at least forms one intermediate, sometimes two. If it rearranges, that's a second intermediate. So it forms a stepwise reaction, unimolecular, order one, rate order one. In the case of SN2s, you do not get rearrangement. SN1s, you get rearrangement if you can. And there's three ways to do that. Know all three ways to do rearrangement of the carbocation. And that means that the smaller the group is, the more likely it is to go through an SN2. The bigger the group is, the more likely it is to go through an SN1. Okay. So that means that primaries and methyl groups only do SN2. Check that box off. Allylics and vinylics don't do either because these are sp2 hybridized. Secondaries can do both. Primary and secondary allylics and benzylics can do both because it can stabilize the charge by using resonance, Tertiaries and tertiary benzylic halides only do SN1. So you can just check that box, tertiary, SN1. Okay. So the last thing I want to talk about here is all the different functional groups we can do. I said, no matter what nucleophile you attack it with, you end up with a different functional group. Hydroxide gives you an alcohol. The alkoxide gives you an ether. The you can get a thiol, thioether, thio. This increases your carbon chain by 1. This increases your carbon chain by 2. This makes an ester, makes an amine, makes an azide. So whatever you're attacking with, you can make a bunch of different functional groups. Okay. All right, I'm going to stop here and take a break, and then we're going to talk about the activity, and we will then move on after that. Okay, it's 11:03. Right. You need to take a bathroom break. This will be it. That gives out hand sanitizer that fits on your little lanyard here. So I'll sanitize my hands before handing out the activity. Okay. Pull up other slides. Okay. So while I was recovering from COVID, I learned that my iPad actually has the same processor that this computer has. And so it's like they have the same strength. But the iPad has a cool thing. It has an adaptive front camera. So if I started using my iPad for that, it would just follow me around the room. And I could do that and it'll just follow me. My FaceTime camera can follow me. So next fall, I'll be doing that, but we'll see. But I haven't got it all moved over to my iPad yet. Okay. All right, couple more minutes here. Well, so just a reminder, the activity is due at midnight tonight. Go ahead and scan it in. I started grading. I did my first, I've graded all the first exam corrections. Those should all be posted. I will look at the second ones today. I haven't looked on them yet. And I've started grading homework too. So I'll grade activities and homework. Hopefully everything will be up to snuff by Friday. That's my goal. Okay. And the exam on Friday will be the second half of 5, 6, and 7. Those are what's going to be focused on. Second half of 5, 6, and 7, and it'll be in class live, and so you'll get to do a little more drawing. So that. All right, so let's talk about the thermodynamics activity here. I want you to go through and think about what we've talked about in the first half and second half of this chapter so far about our thermodynamics. And so I want you to explain to me which reaction is going to go faster and why. And then identify all the different parts of this and tell me what's happening in each part. You can draw little lines and label things like that. And so this is just kind of getting you kind of, to ease into the next one, which is harder. I want you to draw the reaction coordinate diagram for this one-step endothermic reaction. Okay, so I want you to show me where the products begin and what they are. I'm sorry, where the starting minerals begin, where the transition state is, where the intermediates are, where the second transition state, if there is one, and where the products are. And I want you to show that energy difference, showing me that it's endothermic. Okay. On the second one, I want you to do this reaction card, and I'm telling you it's a two-step. And we just talked about carbocations, so you'll see why it's a two-step right here. And I want you to show me that it's exothermic reaction and where that would be. And then I want you for both of these to show me what the rate law would be. Okay, so remember that rate law is defined by how many steps you have, right? So you need to make sure you understand which rate law goes with which program. That's why I want you to draw it out and write those down. Okay, so on this one, I want you to tell me whether it's exo or endogonic. So make sure you questions on the activity. Okay. Again, use your notes. It's I just made this today, so you can't find anything on CHEM, so don't even try. I'm going to start putting little Disney princesses on here so that they have to pull it off CHEM because Disney sues them for that. Anyway, sorry, just a kidding. Aha. All right, so let's go back to chapter 6 and start talking about our next thing. So this is the end of SN1, SN2. Okay, substitution, nucleophilic reaction. Okay, we only have 2 mechanisms, but 100 products we can make. 2 reactions, 100 products we can make. So that's 2 mechanisms, sorry. So that's a really powerful tool. Okay, now I want to talk about the next thing we're going to talk about, which is elimination reaction. We can do substitution, elimination, addition, rearrangement. Those are the 4 types of reactions we can do. I'm going to talk about the second type, which is elimination. So that means we're going to lose 2 molecules. We're going to lose 2 sigma bonds and create a pi bond. Okay, we're going to lose 2 sigma bonds and create a pi bond. Okay, so the reason we want to do this is that this is how we get to the next thing in our chapter, chapter 7, which is alkenes. So we're going to get to how we form alkenes this way. So usually you have to have 2 leaving groups, one on the first carbon, and we're going to call that the alpha carbon, and one on the second carbon, we're going to call that the beta carbon. Okay, alpha and beta. Okay, so the thing we usually use with this is you use a strong base. And what it does is it usually pulls off a proton on one side and a leaving group on the other. Okay, one other way to do that is to lose water. You pull a proton off one side and OH on the other side, and we will lose water. So in the case of here, our alpha carbon is the one with the leaving group that's not hydrogen. So in the case of dehydration, it's OH. In the case of removing HBr, it would be the bromine. That's the alpha carbon, the one with the leaving group on it. The beta carbon is the one with the hydrogen that you're pulling off. It's the one with the hydrogen you're pulling off. Okay. So the alpha carbon and beta carbon are important to identify. Okay. So when we talk about the first thing we're talking about here, we're talking about dehydrohalogenation. So that means hydro meaning hydrogen, halogenation. So we're going to remove HCl, HBr, HI. We're going to remove an acid. So dehydrohalogenation. So we're going to remove an acid with a strong base. And the halogen's always on the alpha carbon. The hydrogen's always on the beta carbon. Okay. So that means we can get to a very easy solution. And because we're removing the hydrogen from the beta carbon, we call this beta elimination. Because we actually had to pull that hydrogen off. We had the leaving group leave, but we had to actually pull the beta off, which is why it's beta elimination. Okay. So we have 2 possibilities of mechanisms. The 2 possibilities of mechanisms are unimolecular, where we have the leaving group leave first, forming a carbocation. That should sound familiar. That sounds like an SN1 reaction. Okay. Then we have an E2, which is bimolecular, meaning that the leaving group is leaving at the same time the base is removing the beta hydrogen. The leaving group is leaving at the same time the base is removing the beta hydrogen. Okay. So when we have this, we have obviously, it's analogous to the SN1, SN2s, right? So we're either forming a carbocation or we're not. Okay, so let's talk about how to predict your your elimination reaction products. Okay, so the first thing we need to think about when we're forming elimination products is we are going to be forming an alkene. So we need to find our alpha carbon first. Our alpha carbon has the leaving group on it, in this case, the halogen. Okay, that's our alpha carbon. Then we have to look for the hydrogens that it could be pulled off on beta carbons. There's usually more than one. So we have to look one carbon over from our leaving group and see which of those have hydrogens on it. Okay, so if we're looking at this one right here, we see that our alpha carbon is this one in the middle because that's the one with the halogen. okay? And our beta carbons are here, here, and here. So is there a favorite one? Well, right now, no, they're all equal, right? We have 3 hydrogens on each of those. So we have a total of 9 beta hydrogens. We have 9 beta hydrogens. And in this case here, because all the beta hydrogens are equivalent, are identical, we can only make one product. Okay, notice our alpha carbon still has those 2 other methyl groups on it, and we've now formed an alkene, a double bond with that other carbon where the beta hydrogen was removed. That's where the pi bond forms. The beta hydrogen was removed. Okay, what if we have 2 different possibilities here? So this beta hydrogen is different because it has a CH2, CH3. This beta hydrogen is different because it's only a CH3. So we have CH2 on one side and a CH3 on the other. So that means we can form 2 different products, right? We can form an elimination product with beta 1, which would give us this. So we have the alpha carbon is going to form the double bond with the methyl group, giving us this product. Or we can go to this one and form this product. So we have 2 constitutional isomers. Okay, they're hooked in different ways. So they have this, they're just constitutional isomers. I also want you to notice this base we're using. What did I call that? I call it a non-nucleophilic base. This is Tb-toxide, non-nucleophilic base. We're going to see this a lot. Okay. So in the case of our 2 different ones, we have that. So how can we predict which of those alkenes is going to be formed more? In theory, you're going to form both of them, but which one are you going to form more? Okay. So we have some rules for that. So when we're talking about that, we're going to see that there's going to be a favorite for which hydrogens are removed versus which beta hydrogens, which set of beta hydrogens are removed. Now, if we're not removing halogens, we call that okay. So let's look at how we would do that as an E2 reaction. Okay. So in the E2 reaction, we have to remove the hydrogen as the leaving group is leaving. Okay. We have to remove the hydrogen as the leaving group is leaving. So our base needs to come in on our beta carbon and start tugging on one of those hydrogens, beta hydrogens. So we're tugging on a beta hydrogen. Okay. When it does that, it's using its electrons to create a new bond with that hydrogen. So the electrons that the hydrogen carbon had are going to be left on the substrate, left on the carbon. And those are the electrons that make the pi cloud. As it's forming that pi cloud, it is taking these 2 electrons here, because we can't have 10 electrons around carbon, giving us our double bond and our product. Okay. So it's a concerted reaction that happens all at once. Base pulls on beta hydrogen, electrons kick in, forming double bond, electrons kick out, forming leaving group, all at once. Okay. So that means our rate law is a second order rate law, just like an SN2 would have been a second order rate law. It's an E2, which is also a second order rate law. Okay. So that means our energy diagram has 1 hump and 1 transition state. But look where the electrons are moving here. We have electrons from the oxygen are tugging at that hydrogen. The electrons from the hydrogen are being shifted to between the alpha and the beta carbons. And the electrons between the carbon and the leaving group, or in this case bromine, are being transferred to the bromine to leave as an ion. Okay, that means we have 1 transition state, 1 product, second order. The other option we have would be the E1 reaction, where we lose the leaving group first, and then we figure out what happens after that. Okay, so in this case right here, we have our leaving group, and again, we have all equivalent beta hydrogens here, so it doesn't matter. And we're going to make 1 product. Okay, and that means we have a first order rate law. Okay, so that should be analogous to our SN1. Okay, so let's look at our mechanism of that. So that means if it's a unimolecular, our first step is to make a carbocation. Make a carbocation. So we're looking for where can we make the best carbocation. And obviously it's going to be on a tertiary, occasionally a secondary substrate. And we're going to form that carbocation, and then even a weak base like water can now pull that proton off. Even a weak base can pull that proton off, and giving us our product. And again, these are all the same beta hydrogens, so we only have one product. Okay, so if we compare and contrast, first order rate law, second order rate, first transition state gets us to our carbocation in our intermediate here. Our intermediates here, that's our carbocation. And then our second transition state here is much lower in energy, meaning it's faster, and therefore goes to products. Okay. So in this case here, we can actually look at its going low because it doesn't have a strong base. So it's waiting to form the carbocation, and then our weak base is going to pull off our proton, generating our alkene. Okay. So just like SN1 and SN2, factors are nucleophilic strength. If you have a good nucleophile, you're probably not going to do elimination reaction. If you have a good nucleophile, you're going to do substitution. If you have a strong base, now you need to start talking about elimination. Strong bases favor elimination. Nucleophilic size. The bigger the base, the more likely it is to form an elimination product. T-butoxide, elimination product, always. And then temperature. It turns out that you can increase one over the other, elimination versus substitution, by playing with the temperature of the system. The number of molecules increases in elimination, so higher temperature promotes elimination. So in the case of this, we want to go, if you have a choice, so let's say you have a base, you run the reaction at 5 degrees and you run the reaction at 100 degrees. 5 degrees, you're going to see some substitution if you have a good nucleophile. 100 degrees, if you have a base, you're going to see more elimination reactions. Now, because entropy is increasing, so heat drives elimination. Heat drives elimination. Then, of course, there's substrate effects. Tertiary alkyl halides typically only do SN1E1 and E2. It'll do E2 with a strong base and E1 and SN1 with a weak base. Now, I said entropy drives elimination. So if we did a tertiary substrate with a weak base at a low temperature, substitution is going to be a major part. If we did that same reaction at a high temperature, elimination is going to be the problem. They're always in competition, but you're going to favor one over the other by temperature. In secondaries, they can actually do all 4 reactions. But when you have a strong nucleophile or a strong base, you typically get substitution if it's more nucleophilic than basic. And you can get elimination if it's a more basic than nucleophilic. And again, colder temperatures promote substitution, higher temperatures promote elimination. Then if we have a strongly hindered base, T-butoxide, it only does E2 because it's too big to be acting as a nucleophile. Okay, and if we have a weak base and nucleophile, it can only do SN1E1, and they're going to be in competition. For primary substrates, we're only going to see SN2 and E2. Okay, we're never going to form a carbocation, and it's whether or not you have a nucleophile or a base. And you have to have a hindered base. Because if you don't have a hindered base, T-butoxide, it'll act as a nucleophile. So if it can act as a nucleophile, it will. If it can't act as a nucleophile, it's going to act as a base and give us our elimination product. Okay. Does that kind of make some sense, you know, with size and kind of energy and everything? Okay, so this kind of goes to this table here. This is the culmination of everything we just talked about. I want to start on the center. strong hindered base, T-butoxide. Everything's E2 except for the methyl group. Why? The methyl group doesn't have a beta carbon. No beta carbon, no beta hydrogen, can't eliminate. So it'll do an SN2 reaction, but it's going to do a very poor job at it. Okay, so let's look at the next column here. Methyls and unhindered primaries, meaning like an ethyl group, will undergo substitution reactions because the nucleophilic strength is good enough. But hindered secondaries and tertiaries will only undergo elimination. If the base can't get in there to act as a nucleophile, it will act as a base on the beta hydrogen, because that's one carbon over. So it's less sterically hindered. So if it can't act as a nucleophile, it'll look for the hydrogen on the beta carbon to get it there. So branch, secondary, and tertiary will undergo elimination reaction with strong, unhindered nucleophiles. Okay, but they have to be strong bases. Let's say they're not good bases, but they're good nucleophiles. So it's more kinetic, right? That means we're going to do SN2 until we get to a tertiary substrate, which can't do SN2. It has to do SN1, and it'll always be in competition with E1. And then let's look at poor nucleophiles like water. No reaction at all until we get to a secondary. That's really slow because it has to wait for that carbocation to form. And then we always have a competition because once you form that carbocation, it can eliminate or move or do stuff. So do we ever want to do an SN1 and E1 reaction? Probably not, because the two reactions are in competition, plus you get carbocation rearrangement. You're going to get like 20 products. So it's very important that we have that kind of culminated in our heads. In fact, I'm going to post an empty version of this on Canvas. And for part of your homework, I want you to fill this out and explain to yourself why each of these boxes are true. Because if you can explain to yourself why each of these boxes is true, you will be able to look at your homework and say, oh, that's a poor nucleophile, that's a secondary substrate, that's a protic solvent, that's, you can just go down the list of 4 things that are important and say, I know what's going to happen here. I know what's going to happen here because I followed the rules on this table. All right, questions on this table and SN1, SN2, E1, and E2. So go ahead and do the thermodynamic. We're not done yet. And I'm going to start chapter 7. And what we're going to do is we're going to see that I want you to find ways to look at the homework and to kind of draw maybe make a different table that makes sense to you. I want you to be able to look at those 4 factors and say, by looking at these 4 factors, it has to be this, because. And if you can get that down in your head, you're going to do great. Okay. If you just try to memorize the table, it's not going to work as well. But if you talk your way through the table, you're going to do great. All right, questions? Okay, I didn't put up the chat, but oh, sorry. All right, so I'm going to start with chapter 7. Okay, and I think we'll have some time to do a review too. So that's good because our next activity is what I call reaction tables. Reaction tables, you're going to hate them, but you're going to love them next semester. Trust me. All right, so the first thing we want to talk about is E and Z nomenclature. And that was on the back of the nomenclature exercise that you saw. And you can go back and do this if you want. You don't have to. We're going to have a different exercise for this. So in the case of alkenes, when we first saw them, we saw that they don't have free rotation, right? So they have stereoisomers, right? And so if you have 2 groups on there, they're either on the same side of the double bond or on opposite sides of the double bond, okay? And if they're on the same sides of the double bond, you call it a cis alkene. And if they're opposite sides, you call it a trans alkene. But what if you have more than 2 things? That definition no longer works. If you have more than 2 things on your double bond, you must use E and Z. Okay, so in the case of Z, Z is called zusammen. Zusammen is German for together, okay? So the way to remember that is if Z groups are on the same side, it is Z. Don't do a better German accent than that. You gotta laugh. All right, yeah. All right. So if they're on the same side, it's a Z isomer. Now, if what's on the same side? The highest priority group on one side of the double bond and the highest priority group on the other side of the double bond. Okay, if the highest priority group on one side of the double bond is on the opposite side, and we call this Entgegen. Okay, if they're on opposite sides, the highest priority group and the highest priority group on opposite sides, we call it E. Okay, so what in the heck do I mean by priority? We use the exact same rules we used for chirality going for 1, 2, 3, and 4. But in this case, we only have to figure out one. The number one priority on each side, okay? So what we're gonna do is we're gonna do one little exercise here, and we're gonna look at this, okay? So on this one right here, we're gonna use those exact same rules, and we're gonna use the rules in the same order. Z number, go out until there's a difference, double bonds and triple bonds and isotopes, okay? Same 4 rules. In this case here, what we're gonna do is we're gonna look at the double bond by first cutting the double bond in half, okay? Because that double bond is gonna tell us if they're on the same side or opposite side, okay? The second thing we're gonna do is we're gonna cut it in half, the other way, okay? So in the case of this, we're gonna figure out the highest priority group on that side. We're gonna assign it 1. What do we do with the other group? Doesn't matter. It's not the highest priority. We don't even have to assign it. Now, let's go to do the same thing on this side. So in this case here, we're going to compare this to this. Hydrogen to bromine, which is higher priority. Bromine, because it's a higher Z number, we can use rule number 1, and so boom, we have that. All right, now let's look at the other side. So we've already looked at that side. Let's look at the other side. And we have a carbon and a chlorine. So we get to stop at rule 1 again. We only look at Z number. And chlorine is the one that's there. So we're going to look at that. So now priority 1 on one side versus priority 1 on the other side. Where are they in respect to the double bond? They are on opposite sides of that double bond. So that means they are Entgegen. So this is E. E. Now, to practice, again, do the back of that nomenclature thing. You'll be able to practice this a lot. So let's look at this one over here. And so if we did the same thing here, we're going to look at this and then this. This is going to be the highest priority group because of rule number 1. This is going to be highest priority because rule number 2. So we can then eliminate all of this and say, here's our line, here's our line. They're on opposite sides of the line. It is E. So we can do the same thing, and all you have to do is keep assigning them as the priority that exact same way. And we'll see that this is Z. And that, let's see, this is a chlorine, this is an oxygen, these are carbons. So yeah, it is also a Z. So go ahead and run that activity just to make sure you got it straight in your head. Okay, so it's fairly easy to do, and we're just going to use all the same rules that we had before. We're going to figure out what the functional group is, the highest priority function group, longest chain, where the substituents are, where the numbering is. And remember that the alkene, both carbons of the alkene have to be in the longest main chain. Okay, so use the exact same rules. The only thing we're going to do is now put an E or Z at the beginning of the name. Okay, yes.
Can you explain what the OH group is higher priority than the CL? Bottom right.
Okay, well, because if we're looking at that, we have to cut it this way first, then
I mean, on the other side.
on the other side. On this one?
Yeah.
Oh, that's wrong. Haha, you are right, because O is 8 and CL is 17. So that is not. This is the higher priority, and so it is an E. Thank you. I'll update my slide. All right, questions on that? Thank you for finding that error. I try hard, I'm not perfect. All right. Okay, so now let's talk about alkenes. So I said before, you have choices of beta hydrogens, right? And so you want to know which alkene you're going to form if you have choices. So it comes down to the stability of the alkenes. So what do we mean by stability of alkenes? Okay, so what we're going to look for here is where is the double bond less reactive? If the double bond is less reactive, then it's more stable. Okay, so that means that we have a couple definitions we need to figure out. First of all, a terminal alkene is at the end of a chain. So imagine double bond. That is what we call a terminal alkene. It's at the end of the thing. So that means that carbon 1 and 2 have the double bond. Now, if we have an internal alkene, it's going to be where neither one of the carbons of the alkene are in the one position. Anywhere else in the chain, just not in the one position. Okay, so a terminal alkene is actually less stable than an internal. Now, what we also figured out is that our E is more stable than our Z. And if you think about it, let's think about, you have two groups in the Z position. They're going to push each other apart, giving us torsional stress here. And if they're opposite each other, they're not going to see each other. So there's no stress. So E is more stable because there's no torsional stress. Okay, there we go. All right. So now you can say, well, that's kind of just, hand waving, literally hand waving. But how can you be sure? Well, we can actually measure it. We can measure the heat given off by hydrogenating an alkene. So we're going to add hydrogen across that double bond, and the heat it liberates tells us how much energy was stored in that double bond. So how much energy was stored in that double bond tells us how much more energy it had or how less stable it was. Okay, so if we just looked for that heat of hydrogenation, the change in enthalpy of our hydrogenation, and we looked at our terminal alkene first. Okay, we'll look at our terminal alkene. It's about 127 kilojoules per mole of heat given off. Okay. But if we could take that terminal alkene and move it to a cis alkene, a Z alkene, it actually doesn't take as much. It only liberates 120 kilojoules per mole. That means it gave off 7 kilojoules per mole less heat. So it was 7 kilojoules per mole more stable. Does that make sense? Less energy stored in the bond, it gives off less heat when we react it. Therefore, it was more stable. And if we do the same thing for the trans version here, we actually give off even less heat, 5 kilojoules less heat. So that torsional interaction is 5 kilojoules per mole less stable. Same groups, 5 kilojoules per mole. Okay, so we actually measure these. These are not empirically derived. These are measured. And we know that terminal alkenes are less stable than cis alkenes. Cis alkenes are less stable than trans alkenes. But we were talking about things with more than 3 things on them, more than 2 things on them. So let's talk about why different things are going to be more stable. First of all, these are now, the carbons we're using are sp2 hybridized. When they were sp3 hybridized, they had 25% S character. And S is smaller, holds things tighter. Okay. These are sp2 hybridized carbons, and they're more able to accept electron density because of the p orbital being unhybridized. Okay, which means electron donating groups can stabilize alkenes through that inductive effect. We already have done that inductive effect in acid base and in stability of carbocations. So that same inductive effect is playing a role here. Okay, so what we're thinking of is that the more things attached to our double bond, the more stable. So let's look at our just alkene by itself. This is just ethylene right here. No carbons, no donations. Those hydrogens don't donate at all. So that's going to be our least stable. It's a terminal alkene. It is least stable. I mean, it has no R group. But here we have one R group. It's slightly more stable because that R group is donating electron density. And then if we had two R groups, but in the cis configuration, it's a little more stable because of donation, but it still has torsional energy. But then we go to the trans, and it's actually more stable. Okay. But look at this. If we have them both on the same sides, it's not as stable as the trans. If you think about it, it's because the things are being spread out. I just want to finish the slide. They're being spread out this way, so there's a little bit of torsion on that one. So that's why this is less stable than the trans here. And then 3 substitutions gives you additional donation. 4 gives you even additional donation. Okay. So the more substituted the alkene, the more stable the alkene. Trans alkenes are more stable than cis alkenes. The more substituted, the more stable. The more trans, the more stable. All right. Thank you very much. I will see you tomorrow. So let's go ahead and pull up my menu again. View. Show meeting controls. I'm going to stop share. I'm going to stop record.